So, good day everyone. Today we will talk about the effects of liquid density, liquid height, and liquid temperature on hydrostatic level measurement and control and closed tank system. So, hydrostatic level measurement, a technical reference for engineers and technicians converting fundamental physics, open and closed tank system, and the effects of key process variables. So the hydrostatic formula: hydrostatic pressure, liquid density, gravitational acceleration is 9.81 miles per second squared, and liquid height above measurement point. Hydrostatic pressure is equals to density times gravity and also times liquid height. For open tank or operating principles and how it works, I will have a example, or I will show you the example video after this presentation. Tank top is open to atmosphere. Atmospheric pressure or PATM acts actually on liquid surface and gauge sensor. For atmospheric pressure component cancel out naturally because P, ATM cancel on both sides. Only the hydrostatic head from the liquid column contributes to the sensor reading. For measurement of open tank, sensor configuration: single pressure transmitter or submersible sensor measure gauge pressure, and direct relationship between pressure reading and liquid height. This is the governing equation. The P sensor is equals to density, gravity, and height level. Measure pressure and converting to height. So, to open or pressurized tank system, operating principle: tank is sealed with vapor space or blanket gas, PB for above liquid. Simple gauge sensor cannot distinguish liquid height from pressure, vapor, or total pressure at the bottom is the hydrostatic bottom and hydrostatic vapor plus density, gravity, and also the height level. So for closed tank differential pressure solution, this is the high pressure port connected to tank bottom reads PB4 plus density, gravity, and height level. And low port connected to vapor space at top reads P vapor, and for result vapor pressure cancels, only liquid head remains. For differential pressure equation, this is the differential pressure equation. Yan. Wet or dry leg arrangements are used on the low pressure line depending on whether the vapor is likely to condense. The effects of liquid height: pressure is directly proportional to liquid height. As liquid rises, weight increases. Proportional pressure rise transmitter or transmitter calibration: LRV at 0% level to 4 milliampere, URV at 100% level to 20 milliamperes. PID controllers use this signal directly for process control. For the liquid density, or effects of liquid density, variable density errors: higher density exerts higher pressure for same height to falsely high reading, and to premature bulb pressure or false alarm. For our lower density, exerts lower pressure for same height to falsely low reading and to risk of the tank overflow. Compensation multi-fluid application required recalibration or dynamic density compensation. For our effects of temperature or thermal expansion and density, temperature rise liquid warm and expands. 2. Density drops, volume plus density decreases. And 2. Pressure unchanged, hydrostatic pressure stays constant. Temperature increase, liquid expands, 2. Density decreases. Physical height may increase but total mass and hydrostatic pressure remains constant. Transmitter fails to register physical height expansion, density induced measurement errors. For the effects of temperature, wet leg and sensor drift, wet leg density variation, ambient temperature changes alter wet leg fluid density, and to zero shift in reading. Sensor thermal drift, extreme temperature cause diaphragm and electronic expansion to zero and span drift. For mitigation, smart transmitter with thermal compensation mitigate these effects. And next, the comparison of open and closed tank system. Their parameters, pressure equation, vapor space, density impact, and temperature impact. Yes. And we proceed to our, for my example, I collect it to YouTube videos. I'm discussing the examples using YouTube videos. Hydrostatic level measurement using a pressure measuring instrument is suitable for measuring the level in a wide variety of vessels. Hydrostatic level measurement makes use of a fundamental physical principle. For example, the deeper a diver dives, the greater the pressure on him. It is completely irrelevant how much volume and mass the liquid has in total. Only the height of the liquid column matters. If we turn this principle around, it becomes clearly that we can easily determine the filling height of any vessel by determining the hydrostatic pressure. Wika offers a variety of solutions for hydrostatic level measurement. The most commonly used solution for this case is submersible pressure sensor. It can be installed without major effort, reaches filling heights or depths of 250 meters, and extremely low maintenance. A special case is the measurement inside sealed vessels. In this case, the gas pressure must also be measured with a good second pressure measuring instrument. If the gas pressure is now subtracted from the lower measured value, the correct filling height can be determined alternatively. This procedure can be carried out with differential pressure measuring instrument, that is, with only one measuring instrument. Yes. And that's all for my first example. Let's proceed to our second example. At how we ended the first part. We'll look at a control loop where a differential pressure transmitter is connected to measure an open vessel level. The high pressure port is connected at 0-inch point, and the low pressure port is vented to atmosphere. We said that pressure in inches of water is equal to relatively density of the liquid multiplied by the height of the surface of the liquid in inches. We talk about converting the resulting inches of water pressure value into any scale that you need, such as PSI, kilopascal, or bar. That works. Just find that if the liquid in the vessel is water, what if the liquid stored in the vessel is not water and doesn't have a relative density of 1? The relative density of liquid will change with temperature. For the sake of simplicity, we will ignore the effects of temperature for now. Interestingly, when the vessel is full at 200 inches, the pressure level or develop is much lower because the liquid has low relative density. That is critical consideration when calibrating the differential pressure transmitter. Let's assume that differential pressure transmitter is calibrated to produce a 4 to 20 milliamps for a liquid level range of 0 inches to 200 inches. So, the major difference between open and closed vessel level measurement is the fact that we need to consider that pressure in the vapor above the liquid in the closed vessel. This vapor pressure exerts a force on a surface of the liquid. So, we can compensate for the vapor pressure by connecting the low pressure side of the differential pressure transmitter to the top of the vessel through a pipe referred to a reference leg. The reference leg may be dry or filled with liquid. If the reference leg is dry, it is commonly referred to as dry leg, and if the leg is filled, it is commonly referred to as wet leg. Dry leg, the vapor system pressure is applied to the high pressure and the low pressure side of the differential pressure transmitter. The same pressure applied on each side basically cancels each other out. Sometimes the reference leg needs to be filled with a fluid. This leg is now referred to as wet leg. There are many reasons for a wet leg, such as avoiding the errors in measurement caused by vapor condensate in the reference leg. Let's look at the example of wet leg system. The differential pressure, as always, will be high pressure minus low pressure, but the resulting differential pressure is not easily to predict because the liquid in the vessel is usually not the same. This is the previous what I've discussed, and a reference leg is used to compensate vapor pressure in closed vessels. And also the dry leg reference leg is caused by a dry leg. A wet leg is reference leg filled. Okay? A reference leg is used to compensate for vapor pressure in closed vessels, and a dry reference leg is called a dry leg. And also, a wet leg is a reference leg filled. Okay? I hope you understand, and I hope you've learned something about this video. Sana nagtugma. And that's all. And thank you.